We move on to the next part of normal distribution, which is standardizing your normal distribution. And basically, every normal distribution curve has the following characteristics, right? Where the mean is at the center, at the peak, whatever mean that is. The area under the curve is 1 because it shows the entire probability. And the height or the spread of the curve is determined by your standard deviation. But we can code this data so that we make every curve into a standard normal curve. What exactly is a standard normal curve? It's a curve where the mean is exactly 0 and the standard deviation is exactly 1. And it sort of gives us an easier way and a more predictable way of finding those probabilities under the graph. So when a random variable x is normally distributed with a mean of mu and a variance of sigma squared, then z, which is another random variable which we are introducing, will be equal to the random variable x, whatever the value of that is, minus mu over the standard deviation. And this form of coding, where you subtract every value by mu and then divide that by standard deviation, that will be a standard normal distribution, which means it will have a mean of 0 and a standard deviation of 1. And what that random variable tells us, that standard value, that z value, will tell us how many standard deviations x is away from the mean. So if it's 1 standard deviation away from the mean, then in your standard normal distribution, your z value will be 1. Let's take an example. Let x be the normally distributed variable, mass of a tomato measured in grams, with a mean of 20, so mu is equal to 20, and standard deviation is equal to 3. We have to find the probability that any particular tomato has mass less than 23 grams. This entire thing can be written like this. X is normally distributed with mean 20 and variance of 3 squared, which is 9. And we have to find the probability that a tomato has less than 23 grams. Changing this into the z random variable, you will use the following formula. Z is equal to the x value minus the mu value over the standard deviation. And the z value that we get will be how many standard deviations x is away from the mean. So in this place, our x value is this 23. So z is equal to 23 minus mu, which is 20, over the standard deviation, which is 3. This will just give us 3 over 3. It will just equal 1. Therefore, our z value is 1, and that tells us that this 23 is 1 standard deviation away from the mean. And then the moment we find that our z value is 1, and we want to find the probability of basically z being less than 1, we can go back to our table and find the value of this thing, which, as we did in the previous lesson, you will go to your z value, which is 1, and there is no second decimal point, therefore your answer will just be 0.8413. So that right there, the probability will be 0.8413. That's going to be your answer. We take a look at another example where we're given that x is normally distributed with a mean of 11, therefore mu is equal to 11, and your sigma squared is equal to 25. So your standard deviation will just be 5, the square root of 25. Then we want to find the probability that x, the random variable x, is less than 18. And to do that, we need to first convert x into your standard normal distribution, which means what we'll have to do is use our formula to find our value of z, which means z is equal to your value of x, which is 18, minus your mu, which is 11, divided by your sigma, which is 5. This will give us 7 over 5, which will give us 1.4. Therefore, what we have right now is P of z less than 1.4, and we can find this by going back to our table and looking for this 1.4 value. Our 1.4 value is right here. our second decimal point is 0, so it's just going to be this probability right here, so 0.9192. Therefore this here is going to be 0.9192. That's going to be the probability of the random variable x being less than 18. Next, we're given a random variable which is normally distributed with a mean of 20, so mu is equal to 20, and a sigma squared of 7. That means sigma, which is standard deviation, is the square root of 7. And we are told to find the probability of x less than 16.6. So x is just normally distributed. We need to first convert it to standard normal distribution so that we can use our table. We can do that by using our formula. Z is equal to x minus mu over sigma. This will give us 16.6, which is the value of our x, minus our mu, which is 20, divided by root of 7, which is our sigma. This will end up giving us negative 1.285 and so on. And we want to find the probability that z is less than negative 1.285. And remember, what visually this looks like is if you have the bell curve, with this being our mean, which is 0, the standard mean, then this is going to be towards the left of it, somewhere here, let's say. And we want to find this as our probability. That's going to be the area that is going to give us our probability. So for that, what we can do is we will take the probability of z less than positive 1.285, but that will be the entire thing here. And remember, that small section, that is this probability here, will be equivalent to this small section. So we'll do 1 minus that, which will give us the probability of z being less than negative 1.285. So we need to find what this is. Probability of z less than 1.285. So we go to 1.2 on our table, then 1.28 on our table, 0.8997. Then we're going to add 5 to it. So 0.8997 plus 9 in the last digit, which will give us 0.9006. Therefore, this probability right here is 0.9006. We're going to do 1 minus that, which will end up giving us 0.0994. And that's going to be our probability that our random variable x is less than 16.6 in this normal distribution. Next, we're given that the random variable x is normally distributed with a mean of 5, so mu is equal to 5, and a standard deviation of square root of 5, because our sigma squared is equal to 5. Then we want to find the probability of x being between 2 and 9. We need to convert it into a z probability. For that, we need to convert this first unit into z and the second unit into z, which will give us how many standard deviations that is away from the mean. So we're going to start off with our formula. Z is equal to x minus mu, so 2 minus mu, which is 5, divided by the standard deviation, which is root of 5. Then on the other hand, we have z is equal to 9 minus 5 over root 5. This first one will give us negative 1.342. This second one will give us 1.789. These are going to be our two z values. So what we have now is a probability of z being between negative 1.342 and 1.789. Z will be between these two values. And this, if you draw it out, it's going to look something like this, where the mean is 0. This is negative 1.342. This is 1.789. and we are finding the area between the two. And this probability right here is going to be the same as us saying the probability of z being less than or equal to 1.789. It will give us the entire area below 1.789. Then you're going to subtract it by this section right here, which is less than the negative. And for that, we'll make it 1 minus the probability of z less than or equal to the positive version, as we have done in the last lesson. So for that, we need to find the probability of z being less than or equal to 1.789, which is just phi of 1.789. Then subtracted by 1 minus phi of 1.342. And so we're going to find these two values of phi, 1.789 and 1.342. For 1.789, we're going to go to 1.7. Then we're going to go to 8, that's our next digit, so 0.9625. Then our next digit is 9, so we're going to add 8 to that. Therefore, we're going to get 0.9625 plus 8 in our last digit, which will give us 0.9633. So this right here is going to be 0.9633 minus 1 minus the phi of 1.342, which we are now finding. 1.3, then the next digit is 4, so 0.9099. Then we're going to add 3 to it since our next digit is 2. So 0.9099 plus 3. 0.9099 plus 3 as our last digit. This is going to give us 0.9102. So here our phi of 1.342 is 0.9102. And we're going to find this as a whole, which will give us the probability to be 0.8735, which is just rounded off to three significant figures, being 0.874. From the previous examples, we have seen these few things. That if you want to find the probability of your variable that is standardly normally distributed between two positive z values, a and b, then you just take the phi value of b, it's going to be everything up to here, minus the phi value of a. So you're subtracting this, which leaves you with this blue section. Then what if one of them was negative? This was just the example we did, which ended up being the phi value of b, which gives us all the area to the left, minus 1 minus the phi value of a. And if you rewrite this, we get phi value of b minus 1 plus phi value of a, which just gives us phi value of b plus phi value of a minus 1. Finally, if you have something like this, this just expands from this thing here, where if this phi of b was phi of a instead, you would have phi of a plus phi of a minus 1, which gives us 2 phi of a minus 1. So these were some useful results that we got from the previous worked examples that we just did. Finally, we are given a random variable y, which is normally distributed with a value of mu, which is unknown, and a value of sigma squared, the variance. We are told that the probability of y less than 10 is 0.75. The probability of y greater or equal to 12 is 0.1. We have to find the values of mu and sigma. So firstly, we need to convert these into our z values. So z will equal to the random variable, which is 10, minus the mu over sigma. At the same time, z is equal to 12 minus mu over sigma. Here we are looking at below that 10, which means if it looks something like this, and we want 75% of the area shaded, because that's what that means. The probability is 0.75. That means we are shading it such that we get 0.75. that is going to be more than the mean, the center, which means that here our z is positive. The y value of 10 gives us a positive z, which means the mu is less than 10. And since the mu is less than 10, then the mu is obviously less than 12 as well. That means here even the z is positive. Why is this important to note? Is because our table of values only gives us positive values of z. So if it's negative, which we did in the previous lesson, we had an example like that, we take a different case to do it. And what this means is that, again, we have our standard normal distribution, and we have a specific value such that greater than that, we have only shaded 0.1 of the area. That 0.1 is a probability. That means to the left of it we have 0.9. This is a very crucial thing here. That means the probability of y less than 12 is going to equal to 0.9. We can use this information that is going to be meaningful. What this means is that the phi of z for the z1 is equal to 0.75, and the phi of z for the z2 is equal to 0.9, as we can see here. And this came from the fact that 1 minus the phi of z is equal to 0.1 from this original value here. So what we're finding is just these two values of z, the ones that give us a probability of 0.75 and the one that gives us a probability of 0.9. So we go back into our table and we see what z value gives us a probability of 0.75 and what z value gives us a probability of 0.9. So when we're looking for 0.75 in our table, the probability side of things, we see that it's going to be between these two. We're going to take the lower number, which means we have 0.67 currently, and we want to add 14 to it to get to 0.5. Because we have 0.7486, we want to add 14 to that to get 0.7500, which is the probability that we require. The closest thing we have to 14 is 13. And so we want to add our 13, which will give us our last digit of our z value to be 4. So our z value will be 0.674. So here our z value is 0.674. We then move on to the other one, where we want the probability to be 0.9 for that specific z value. Go back to our table. We want it to be 0.9, which will be between these two. So we take the lower one here, which is 1.28 currently. We want to add 3 to that. If we add 3 to that, we get 0.9000. And if we go to our adding thing, 3 will be between this 1 and 2. Which means we can interpolate and we sort of get it that our 1.5 will give us that 3. Therefore, what we'll have is 1.28, which you get 0.8997. Then our last digit is going to be not 1, not 2, but the middle. So 1.5. And that's going to be the z value that gives us the probability to be 0.9 below it. So 1.2815. Therefore, our z value is going to be 1.2815. And with that, we get two equations. From this, we can replace our z, which is 0.674. So 0.674 is equal to 10 minus mu over sigma. And on the other hand, we have this one, which gives us 1.2815, which is our new z value, z2, is equal to 12 minus mu over sigma. What we have is two equations. with two variables, mu and sigma, and we can simultaneously solve them. So for that, we can cross multiply this way, where we exchange the denominator and the numerator. And for both of them, we'll get that sigma is equal to 10 minus mu over 0.674, and sigma is equal to 12 minus mu over 1.2815. This will end up giving us 10 minus mu over 0.674 is equal to 12 minus mu over 1.2815. Then we can cross multiply and solve for mu here. We will get 12.815 minus 1.2815 mu is equal to 12 times 0.674, which is 8.088, minus mu times 0.674, which is 0.674 mu. And from this equation here, we get that the value of mu is going to be 7.781. That will be our value of mu, and we can put that into our standard deviation formula that we just got when we made sigma the subject, and that sigma will end up becoming 10 minus 7.781 divided by 0.674, which gives us 3.292. That's going to be the value of sigma, and that's going to be the value of mu.